Okay, we're going to start 5.6 today. Okay, properties of a linear relation. So remember that that means, and I'm being redundant here, but a straight line, a graph that has a straight line. Okay, and many of you've seen these represented in many different ways. One of them would be sort of a table of values. Okay, this is your x, this is your y, and we know this is linear, okay, because these increments on the x side are going up by 100, which is a steady rate, and the cost is going up by 20, okay, so that makes it linear. Okay, it means if we graph this thing, we're going to get a line that looks like this. Okay, we can take these same values and we can set them up as ordered pairs. And the way you can check to see if a set of ordered pairs is describing a linear relation is exactly the same as this. Okay, this we look at vertically, this we're going to look at horizontally. My x is going up by 100, by 100, by 100, by 100. My y value is going up by 20, 20, 20. So therefore, linear. Okay, a graph is obviously the most simple way to see that. Okay, because we can just see it's a straight line, and so we can say yes. Okay, obviously. Okay. And what we're going to introduce here is we've called this rate of change in the past, but we're going to remind ourselves that now we're going to call this slope, which is going to now be represented by the letter m. Okay, so a change in dependent, so the change in y over the change in x. Okay, and also as an equation. So we know that something is linear when we see the equation, and one of the most important things, okay, to know is that we can have no exponents. The graph of something with exponents in it is going to look like this, okay? So not a straight line. So y is equal to, and then we're going to start getting comfortable using this, mx plus b. So this is where it crosses the y-axis. This is going to be our slope, okay? So dependent variable, okay, is equal to the independent variable times slope plus the initial amount. And this could be 0 because we can have an equation that crosses the y-axis at 0, right? Starts at the point of origin. Okay, so that was just sort of a review. Okay, so now we're going to determine whether a table of values represents a linear relation. So all we do is we check the increments, going up by 5, up by 5, up by 5. And then over here, this went up by 9, went up by 9, went up by 9, went up by 9. So we'd say yes, that's linear, okay? Since both changes in variables are constant, it represents a linear relation. Okay, so now we're going to do a non-example. Up by 5, up by 5, up by 5. Looks good, but you can't just check just the x values. Up by 75 and then up by 225. You don't even do the rest. As soon as there's one, okay, that is not constant, then we just say no, not a linear relation. Okay, so you can go ahead and try these, and in the notes, I will have these answered. You can take a look at it. Okay, the teacher notes that will be posted. Okay, so now example number 2, we can determine whether an equation represents a linear relation, so we could graph each equation. Okay, and now clearly I've already graphed this, and you know right away, you can just default right to that. You can say, well, of course that's linear, it's a straight line. Okay, you could also, now that we've learned about this, you could say, well, I can see that that equation represents a linear relation, so I know. But we're going to go through the whole motion. So I would have given you this equation. You would have picked some x values, your independent values that you're allowed to pick. Normally, okay, in grade 9, I always picked 0, 1, 2, negative 2, negative 1, 0, 1, and 2. So a couple of negative, a 0, and then a couple on the positive side. And what I've done here is I've just shown you the work. So a negative times a negative is a positive 6, plus 25 is 31. And so over here is really just your y side of the table of values. And then I posted them. Or I'm sorry, I plotted them. And so I got a linear relation. So does it represent a linear relation? Indeed it does. Okay, now right away, remember we just talked about this. This contains an exponent, so we know it's not going to be linear. Okay, so I plugged it in. The reason why that happens is a negative 2 squared is a positive 4, and a 2 squared is a positive 4. So we end up getting the same values for here, and what we end up getting is a parabola shape, right? So you can see clearly that that's not going to be. Okay, now these ones kind of spook kids, and I don't know why. Y is equal to 5, so that means no matter what we pick for our independent values, our y values are always going to be 5. So remember again, we're creating ordered pairs here. 0 and 5, 1 and 5, 2 and 5. And if we put those points on a graph, here they are, and we get a horizontal line, okay? Is it a straight line? You bet. So it's linear. It doesn't matter. It doesn't have to be oblique. Doesn't have to look like this to be linear, okay? That's indeed a straight line. So x is equal to 1. So our independent values are given to us, 1, 1, and 1, and then we just slap any ones we one on there. Now we're not going to pick 1,000, 10 million, and negative 980 because how are we going to graph those, right? So keep it real. Okay, negative 1, 0, and 1. We plot those, we get a straight line. Okay, is it linear? Yes, we got a straight line. Okay, so now you try. X is equal to negative 2. So remember, we're going to make a table of values, negative 2, negative 2, negative 2, and then just pick something really simple like 0, 1, and 2, remembering that those turn into ordered pairs. So negative 2 and 0, negative 2 and 1, negative 2 and 2, and you can see that it's indeed linear, okay? Okay, so now we're going to have an oblique line. How do we know that? We have an x and a y in the equation. So again, we're just going to pick simple, negative 1, 0, and 1. So when I substitute these in, negative 1 plus 5 is 4, 0 plus 5 is 5, and 1 plus 5 is 6. Those are our ordered pairs. Negative 1 and 4. 1, 2, 3, 4. 0 and 5. 1 and 6. Did we get a straight line? Yes, so that is linear. Okay, y is equal to 5. Okay, that was just an example to remember y is always going to be 5, and then we pick 0, 1, and 2, or whatever numbers you want there. 0 and 5, 1, 2, 3, 4, 5, 1 and 5, 2 and 5, and we're going to get a horizontal line, but it's still straight, so we'd say yes, linear. Okay, so I'm going to stop there, post this video. We're going to do a little bit of an assignment on this, and then I'm going to finish up these notes here, determining the rate of change. So remember, we're going to start to call that slope, which is going to be sort of a segue into our next unit, which is called, go figure, slope.